So this is a quick video just to try and go over stationary points, turning points, and inflection points. So let's go over the definitions to start off with. So a stationary point is a point where the gradient dy by dx equals 0. Now this is different from a turning point. Simply because at a turning point it does imply that we have the gradient equal to 0, but it also implies that dy by dx changes sign. And I'll give you a specific example of why that's different. And then the last one here is an inflection point. So an inflection point is where we have the second order differential, d squared y over dx squared, equal to 0. So let's look over some examples of where those are the same and where those are different. So in the case of a curve like a quadratic, let's go y equals x squared or something like that. So we've got a quadratic like this. Imagine in a quadratic like this my gradient is going to go from something very steep. So let's draw a couple of lines on here just so that we get an idea of what's going on. So let's say that this here has gradient that looks very steep. Let's go for minus 5. And then if we were to measure the gradient at the next stage, slightly further down, let's go to here, that only might have gradient minus 1. And then if we were to do the next part of the gradient, let's go right at the bottom, that would have gradient 0, and then we'd start increasing again. So we've gone from red, let's use blues and purples. So then we might start going up again, and so we might have the gradient here, and let's say, well, let's do it slightly steeper. Let's say that's gradient 2, and then let's do a purple one that's extremely steep like that. And so that might have gradient 6, something like that. So we've gone from our gradients at these stages. So let's write down a table for dy by dx. So for dy by dx here, if we can imagine a little grid table, the gradient at at the red line point here is minus 5, then we're going to minus 1, then we're going to 0, then to 2, then to 6. And so throughout this curve, as we're moving along this curve from left to right, our gradient is increasing. And our gradient also changes sign. So we see it goes from negative to positive. And so therefore, in this case, our stationary point and our turning point exists at the bottom of the curve. So our stationary point equals our turning point. Or a stationary point implies our turning point, or let's say they're both equivalent. So that's my equivalent sign, turning point. In this case. Yeah? Or they both equal each other at this point. Whereas if I were to choose a different curve, and by the way, since this goes from negative to positive and it's increasing the whole time, we do not have an inflection point. And also gradient increasing. So maybe it'd be best if we write them down one after the other. Stationary point, duplicate, turning point. So this curve here has a stationary point. It also has a turning point, but does it have an inflection point? Nope, because throughout the whole period here, we have a curve that is increasing in gradients. Okay, let's do another case which includes another two of these curves. So if you've got some cubic function, let's pick a cubic function that looks like this, or let's give it a nicer curve like that. So let's call that my cubic. It's some y cubed type function, and despite how bad my drawing is, let's say that at about that point there, we're going to get to 0. Doesn't really look like it, but let's just say the gradient gets to 0 there. And let's continue our graph. So let's start with our reds. So this line here might have gradient 6. Let's draw another one, an orange line. This gradient of the line here might have gradient 1. And then let's go for our blues and purples. Gradient this line here might have gradient 2. And then finally, let's go for, I think we finished on purple last time. Let's say that this one here is gradient 5 or something like that. And so it's increasing throughout the period of this curve. So again, we're moving from left to right. And so in this case of this curve, our gradient dy by dx is going from 6 to 1 to 0 to 2 to 5. Minus 6, sorry. Positive 6. No, they're all positive. From 6 to 1 to 0 to 2 to 5, they're all positive. And so this is going from positive to positive. It's not changing from negative to positive. And therefore, although it's a stationary point because we've got the point 0, it is not a turning point. However, there's something that this curve is doing that the other one wasn't, is that it is increasing up until this point here. So, no, decreasing, gradient is decreasing up until this point. However, from that point onwards, the gradient is increasing. And so in this case here, because the gradient goes from decreasing 6 to 1, we're going down by 5, down another 1, and then up 2, and then up 5. So, we can almost think of our changes in a different color. We're running out of colors. Let's go -5, -1, and now +2, and now +3. Whereas in this case here, we're just decreasing the whole time. We're increasing the whole time. So +4, +1, +2, +4. So it's the change of the change. And that's the idea of our gradient function, because remember that d is basically a sort of summation of our triangle, of our change, basically. So change in y over our change in x. And so this is the change of the change in y over the change of the change in x, which all sounds a bit confusing. But in this case here, as I was saying, stationary point, yes, we got that point there. Turning point, no, because it's going from positive to positive. So no turning point. So we can cross that one. And then the last one that we do have is an inflection point. Because in this case here, we are inflecting. So it's got both of those, but not the other one. Now, let's pick another example, and that could be a curve that goes from, we're just going to focus on, let's do it slightly thinner. It's going down, 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 and then like that. But let's say it's not quite getting to a 0 gradient. It's just going to continue going downwards, and it's going to continue going upwards. Then, if we start measuring the gradients here, let's say that my gradient in the red up here starts at, looks like something like, we'll call it 1. We'll stick with our 1s, and we'll stick with simple numbers. 1, then this stage here, this stage here, we've got, technically, sorry, it's -1. -1, then we've got -2, but then after -2, our gradient starts increasing again. So we'd get -1 again. Well, we've had -1 before. And then our purple one here at the end, we'll call that, let's call it a half. Why not? A half. Gradient of a half. And so if we were to think about our gradients at these points, dy by dx, well, we're going from -1 to -2 to -1 again, and then finally ending up with a half. And so let's think about what's happening here. Well, we're decreasing to -2 by -1, but then we're suddenly increasing again, and then we're increasing by 3/2. And so we're actually changing there from a negative change to a positive change, and so there must be a point where the change is at 0. And so therefore there will be, in this curve, somewhere over the rainbow, a dy over dx, d squared y over dx squared, that is equal to 0. And because the gradient here doesn't ever get to 0, let's say that my gradient there really is, at this point, dy by dx equals -2. But it doesn't get to 0. This here is the lowest point that my gradient gets to. It's my lowest that the gradient gets to. And because that's the lowest that the gradient gets to, it's not going to get to 0. And so therefore, if we think about these three again, stationary point, turning point, inflection point, we are going from oh sorry, it's -1/2. -1/2. Sorry, and so this here would be +1/2. And it's not quite going to reach 0. We're going to ignore that for now. So in this case here, stationary point, well, there's no point there where gradient equals 0. And so therefore, do we have a stationary point? No, we don't. Do we have a turning point? Well, if we look carefully here, our gradient is decreasing up until this point, and then the gradient suddenly starts increasing. And because it goes from decreasing to increasing, and I'm looking at the brown numbers here, or the differences in between, we do have an inflection point. However, because all of these here are negative, do we see they're all negative numbers, we haven't got a change in sign of the gradient, and so therefore there is no turning point as well. So these are three different examples where we have a gradient is increasing, and so therefore eventually we're going to cross through 0, and so we're going to have a stationary point and a turning point. But we're not going to have an inflection point. In this case here, the gradient is increasing, and then at some stage it starts decreasing. Whereas here we're increasing the whole way through. And so therefore it doesn't change sign, and so therefore we don't have a turning point. Inflection point here, we are decreasing and then increasing, but we're not quite getting to 0. And so therefore, because it never changes sign from the negative, we don't have a stationary point or a turning point, but we do have an inflection point. If that makes sense. I hope that kind of clears things up. Actually, let me go over a quick example from one of those questions that's on the sheet. Let me find it, and then we can go over one of those questions, and that might just be helpful to a few of us while I've got this recording running. So if I go on to Manage Back and I have a look, sorry, just going to log in quickly, and then we'll pick one of these equations and we'll do the question, just because I'm on here now, so I might as well. Okay, so applications of differentiation. I'm going to pick one of those examples. We did 3 in the lesson. Let's do another one. Let's do example, as I think it becomes clearer when we do examples. Let's do example 4. So example 4, Example 4 says that f of x in this case equals x to the 4 minus 2x squared. So what we're going to look at is we're going to look at the increasing and decreasing intervals. So let me add that quickly to our worksheet. Like that. Use the photo. And then we should be able to just fill in the gaps here. So we're going to look at the increasing and decreasing intervals. We're going to look at the local minimum and local maximum points. And we're going to look at the inflection points and when those crop up by doing some of our rules. So step 1 that you're given on the sheet is that we have to differentiate to find our critical points. Our critical points is where the gradient equals 0. So step 1, we need the differential to be equal to 0, and so therefore we need f dashed of x, which would be times by the power, take 1 away, times by the power, take 1 away, and we need that equal to 0. So when does that equal 0? Well, let's figure out our 4s because they've both got 4. So we've really got x cubed minus x equals 0. Try factorizing that, take x outside, x minus, remember we can't get rid of x just by cancelling it down because that is in fact a solution. Think about it, we've got x minus 1, x plus 1 equals 0. So our solutions include 0. We get minus 1, 0, and 1. So that there is step 1. Step 2, think about a number line. Put your numbers in a row. So let's start at x equals minus 1, and then let's go to 0, and then let's go to 1. So pick a value to try for your differential. I'm going to try, let's try plus 2. I'm going to try this. Let's put try. Let's try 2. And let's see what my differential turns up as. So, because we know that at all these points here, our gradient equals 0. So dy by dx. Let's actually put our these here my x values, and these here my gradients, dy by dx. And so in this case here, the gradient when x is minus 1 is 0, 0, 0. Those are my critical values. So I'm trying 2, and then I should be able to work out what's in between. So if I try 2, I would get a gradient of plugging 2 into here, 2 into there, 2 into there. So 2 cubed is 8, 4 times 2 is 32. 32 minus 4 times 2, well, that's 32 minus 8, which is 3 times 8, which is 24. So we get an answer here of 24. And so therefore that's greater than 0. So we're gradient dy by dx is greater than 0, then we can assume that the gradient here is going to be less than 0, gradient here is going to be greater than 0. Unless we have a really strange curve that does this, then we get a level, and then this, and then we get a level, and then this, and then we get another level, which I think is highly unlikely. But, you know, it could happen. You could get a sort of set of steps. I couldn't think of a function off the top of my head that might do that. I think of one that might just do one step, but I think in this case we haven't got one step. So in reality, you don't need to try lots of other values. You could try 1 in every single one of these gaps. So you might try 4 values, but in 99 cases out of 100, you can just try 1, and then you can assume that it alternates. And so my gradient here would be less than 0. Less than 0, greater than, less than, greater than. Okay, makes sense. So therefore, find the derivative for the function in each test point. Find the derivative of the function in each test point. Okay. So in these points before minus 1, we know that our gradient is getting steeper. It's getting is less than 0, so it's going to go like that. After 0, it's going to go, after -1, x equals -1 is going to go up. Then it's going to go, because it's less than 0, back down again, and then back up again. And so this here is our step 3. And really this kind of includes our step 4. No, it doesn't. Step 4 is about minimum and maximum points. But okay, step 3, we found that. So that means that we can start filling out part of our table. Increasing intervals, well, we know it's increasing when x is less than -1. We also know it's increasing when x is... x is increasing when x is between -1 and 0. -1, 0. It's also increasing when x is between or just greater than 1. Okay? Decreasing intervals, we're looking for the downward slope. So x is less than -1, and the other one there is x is between 0 and 1. So that's our first 2 stages of our grid filled out. So if I have enough space to put them all on, would prefer to use parallel lines, duplicate. And then let's try fill this out, this table out here. So increasing, decreasing, increasing, decreasing. Well, we can assume that these points here, that's going to be a minimum, that's going to be a maximum, and that's going to be a minimum. The one thing that we can't be sure of is whether, as I said, there isn't a point where there's actually a stage where we're not going less than 0, we're going on an inflection like that. And so that's why it's always worth checking your second differential or testing all the values in between. So we can find our second order differential, but that's step 5. Let's do this is step 4 really, minimum, maximum. Step 4 is therefore we have a minimum, x equals -1 is a minimum, maximum x equals 0, and then another minimum, and x equals 1. So that was step 4 on your sheet. Step 5, now we're doing our second order differentials. So to locate the inflection points, we need to differentiate again. And so we have our differential, which we found out was 4x cubed minus 4x. So if the differential, double differential, f double dashed of x is going to be 12x squared minus 4, and we want to set that equal to 0 to find our critical points or our inflection points, and so therefore our x cubed this is going to get nasty. Oh, it's x squared. Sorry, not that nasty. X squared is going to be 1 over 3. X is going to be plus or minus 1 over the square root of 3. Okay, well that kind of makes sense, because at some point here we're going to go from increasing gradient to decreasing gradient, and then at some point here we're going to go back to increasing in our gradients. But let's do that more in step 5. So step 5 here, let's look at our critical points. So sorry, step 6, let's look at our critical points. So on a number line, exactly the same as we did before, we've got our values for x. So our value for x is going to be minus 1 over square root 3. Next value of x is going to be 1 over square root 3. What's going to happen in between here if I try my second order differential, d squared y over dx squared, well then if I plug in, let's plug in 0. If I plug in 0 here, I'm going to get minus 4, so d squared y over dx squared is going to be less than 0, so therefore I can kind of assume these ones here are going to be greater than 0, and this one here is going to be greater than 0. And so that gives us our step 6. And so this means that before this stage here, we can imagine that we're going to be, because the gradient is greater than 0, we're going to be concave. After that point there, we're going to go into convex. Sorry, the convex and then concave, because it's going to look like a cave if it continued, and then back to convex. So this is convex, concave, convex. And so that there was our step 7. Style black. I see a red door and I want it painted black. So step 7. So concave, convex, concave. Or convex, concave, convex. A lot of words. And now we can really start to sketch our graph. We've kind of got the shape now, but we can start to sketch it. So in step 8, let's actually summarize our values. Is what they're saying for step 8. Well, local minimum, local maximum values. Local minimum we worked out was x equals minus 1. And the other one was x equals 1. Local maximum values, it's just x equals 0. Inflection points, for this curve, inflection points for this curve are going to be at x equals plus or minus square root 1 over square root 3, which is square root 3 over 3. And then the concave upwards and downwards. Concave is, so cave up, x is therefore between the 2 points, so minus 1 over square root 3 and 1 over square root 3. And then concave downwards, x equals less than minus 1 over square root 3, and x equals greater than 1 over square root 3. And so we've got all our points, and then they ask you just to sketch the graph. So we've pretty much already got a sketch, but you know, it's going to look something like that. I'm going to leave it there. Hope you enjoyed the video and found that kind of helpful, and explained a few things for the test on Monday. I'm going to upload the PDF file as well with this. But that there is those 3 terms: stationary point, turning point, and inflection point, summarized in a nutshell. Hope that was helpful. The one thing actually I'd like to quickly mention is that at all of these points here, if my second order differential is greater than 0, that always implies a minimum point. And if my second order differential is greater than 0, that always implies a maximum point. And so if you want to double check whether a point is minimum or maximum, and you don't want to do it with a whole load of inflection points, it's actually more helpful if you just got a quadratic. So imagine if I've got y equals x squared, and I want to check if this is a minimum or a maximum. Let's do a stranger function, y equals x squared plus 2x plus 1. It's going to look like a quadratic of some sort, and I want to check if I've got a minimum point or a maximum point here. To find my gradient, dy by dx, I would just get 2x plus 2. Well, I can work out what the gradient here would be. It would be x equals -1 when I've got my minimum or my maximum point, but I have a stationary point. And if I were to do the second order differential of that, and to check it, I would get 2. Well, 2 is greater than 0, which implies that this here is what? Well, let's look up at what I said. If it's second order differential is greater than 0, which it is, we have a minimum point. And so this here is a minimum point. And so therefore, the graph is going to look, well, the curve is going to look something like that, with an upwards shape. So it's going to be convex. There we go.